All right, the next section we're going to look at here is called, it's section 7.3, but use similar right triangles. So I want to jump to the theorem first, and the color coding on the theorem is pretty useful here. It says, if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So first of all, altitude. So here's the altitude. I'll kind of outline it. The altitude is a perpendicular segment from a vertex to its opposite side. Okay, so a lot of times we call that the height. It doesn't have to be the height, but it could be considered the height. There's actually several different segments we could call the height. So if we have a right triangle here, okay, so I want you to look at the big right triangle where an altitude is drawn. So do you see how it splits it into two more triangles? I have a triangle on the left and a smaller one on the right. So those two triangles are shown below. So the red one is the smaller one on the left, the blue one here is on the right, and then the original large triangle is in black. All right, so it says here that the two triangles formed are similar to the original. Okay, so the red one and the blue one are similar to the original black one and to each other. So that means the red one and blue one are similar to each other. So they're all three similar to each other. So I've got several statements here. So our takeaway is we're going to use this idea to find missing side lengths. So what that means is the ratio of corresponding sides can be put into a proportion so we can find the different lengths. All right, so let's look at number one here. It says to find the length, we're finding the length of the altitude. So identify the similar triangles in the diagram, then find the value of x. So here's what I want us to begin with. Let's re-sketch all three triangles so they are, rotated around and oriented the same way. So I'm going to maybe start here with this guy right here, ABD. So I'm going to make it, this is going to be the smallest one. So I'm going to try to make them, small, medium, and large. So here's A, B, D. I'm also going to add as much information like all the numbers I can. So here is 7.3. This is H. I don't know what AD is. All right, let's take the one here on the right. So I'm going to make it a little bit bigger, but I'm going to orient it the same way where the 90 is in the lower right corner. So when I do that, that's point D. If I kind of rotate it around mentally, that means C comes up to the top, and then this is B over here. Now, what information do I have on this one? So I know that H is right here, which is segment BD. I also know the hypotenuse is 12.3, so I can add 12.3. And that's it. I don't know CD. All right, now let's take the largest triangle. Right angle here. So that's B. C would be up here, and then A. I know that AB is 7.3 and BC 12.3. Okay, now based on our theorem above, all three of these triangles are similar. So what I can do is take any of the three, or really I want to take two at a time, so that I can make a proportion and solve for x, or I guess really h. That should say h. All right, let's see. So here, let me do a little highlighting. H is right here, but see how I don't have anything here, but I do have 12.3 here. So I could maybe look at I could maybe look at H and 12.3, but then 7.3 doesn't go with anything, and AD doesn't have anything here, but it has 7.3 there. Okay, so I'm not going to use H there. Here's another H, and I have a 7.3 on a corresponding side. Oh, wait a minute. I missed something on my picture. Let me go back. I missed 14.6 right here on AC. Oops. Let's add that in there. Okay, so that means then, let me change my color here. I have a number here and a number here. So I can use the green and the blue triangle and set up a proportion and ratio those sides to solve for h. So I can set up h over 7.3 equals 12.3 over 14.6. Okay, so this is one potential setup. So if I go to solve, 14.6h equals 7.3 times 12.3, 89.79. And then we're going to divide off that 14.6. I get 6.15. Okay, so I was able to take the idea that when I have this altitude right here, when I have this altitude on the large triangle, it creates basically 3 triangles that are similar, which gives me lots of options to find my missing lengths. Okay, so that could potentially be a lengthy process to try to resketch everything and then ratio. So we do have a couple of theorems that are going to allow us to take this particular setup and jump straight to a proportion so I can solve things a little quicker. All right, so let's go to the next page. I want to talk about this idea of geometric mean for a second, because it's not something that we've spent or you hear a lot about in middle school. You probably briefly talked about it. So geometric mean, this first sentence here says, x is the geometric mean of a and b if and only if you have this proportion. So if and only if. So see how x is going to be diagonally across from itself. So let me back up and have you look at geometric mean another way. So I'm going to give you, if I gave you this, 1 and then some kind of number and then 4. And so the number the blank you're trying to fill in, you're trying to give me a number so that when you ratio 1 to my new number, it's the same as my new number to 4. Okay, so when you do 1 over something, it's going to be the same as that same something over 4, which is kind of what I have here. See how this says x and x? In a way, that's what I've set up. So if you think about it, you probably could come up with the fact that the number we're looking for is 2. Because if I do 1 over 2, which is a half, and 2 over 4 also reduces to a half. Okay, so a quick way to find that, let me back up, is what if I had 1 over x equals x over 4? Well, I could cross multiply and solve this and get 2 pretty quickly. So x times x is x squared. 1 times 4 is 4. Take the square root of both sides, and we get 2. Okay, so the geometric mean is a number that when it goes into a ratio, the two ratios are equal. And so really what we look at is we set up a proportion and then we can solve. So we have geometric mean proportions that we're going to use in these two theorems. Okay, number 1 here. This is called the altitude theorem, so the geometric mean of the altitude. So from this theorem, in a right triangle, the altitude from the right angle to the hypotenuse is the geometric mean. All right, so we need a diagram here. Let me try to draw that original kind of picture where you have a right triangle, 90. I have a height and altitude. Oops, no, I want to put, I'm going to put H. Okay, so do you see how the H splits? Let me do a different color. I have the altitude is splitting the hypotenuse of the original triangle into 2 parts. I'm going to highlight them in purple and green. All right, so I'm going to call this part 1. And then this will be part 2. So what I'm looking at here is I am looking at the altitude of the big triangle. The altitude is cutting the hypotenuse of the big triangle into two parts here. So my geometric mean theorem of the altitude allows me to put the altitude is going to be the repeating portion, okay? And so we say that we're going to find the geometric mean of the altitude. So that means it's going to be the same number is going to be equal in two ratios. So I'm going to have part 1 of the hypotenuse in one of the ratios in part 2. Okay, so what I mean by that is let's throw some numbers on there. Let's say that part 1 of the hypotenuse is 5 and part 2 is 10, therefore the whole thing's 15. So my setup might be 5 over, let's say h instead of x, equals h over 10. And so I want to find what number is going to satisfy that ratio. Okay. Now, the second one is the geometric mean of the leg. And so when we're talking about these theorems, we're always talking about the altitude or the leg of the big right triangle. So let me get another diagram in here. Let's kind of draw that same one. Right triangle, altitude, even though we don't really need the altitude on this one as much. Okay, so for this theorem, either leg of the original right triangle is used for the geometric mean. So here's what I want you to see. Leg and leg, when we're doing the geometric mean of a value, it's the same value repeated. So let's do this. Let me kind of color code. So I'm going to put X for my leg, okay? Now, the two items I need are the hypotenuse of the whole triangle. All right, so let's say that the whole hypotenuse here is 20, okay? And then I need the part of the hypotenuse that is touching the leg we're doing the geometric mean of. So let's say that this is 5 units right here. So then I would have the 20 over the leg equals the leg over the 5. So I've got, when I'm trying to find either leg, I either am going to have this leg or this leg. So I'm going to be doing the geometric mean of the leg, which means that's the number we're looking for. And in the other part of the proportion, I need the entire hypotenuse, and then I need just the section of the hypotenuse touching the leg I want. So for example, if I had an X over here, I would have to know this section of the hypotenuse and the whole thing. Now, all of these like formulas and shortcuts are really reinforcing this process. So you could theoretically ratio your 3 similar triangles and get to your answer. It just will take you a bit longer, and sometimes it could be kind of cumbersome to determine, okay, which sides are corresponding. Okay, I'm actually going to stop this video. I don't want it to get too long, and then when I come back, I'm going to